Alistair is a research data engineer at Manaaki Whenua Landcare Research, which, for the visitors, that's a government-owned environmental science research institute. And his work encompasses the operational systems there at Manaaki Whenua and the national international initiatives to build an integrated commons of environmental observation data. Prior to this, he occupied a similar role at the Geological Survey of Victoria in Australia, and there he was actively involved in the development of the geoscience and earth resource markup languages and their implementation as part of the One Geology and OSCOPE initiatives. And if he tries very hard, he can dimly recall starting professional life as an exploration geologist in Western Australia. Please welcome Alistair Ritchie.
Thanks, Richard. I'm used to people walking out while I speak, not walking in. This is a nice novel experience for me. But it's, and to be honest, I really don't enjoy public speaking. And after Richard's and Mike's effort, actually recovering from the missing speaker before lunch, I'm quite keen to actually just run now and let them handle it. I think you can do the slides and Mike can interpret it through the medium of dance. I think there's some potential there. Okay, so what I'm going to talk about today is a couple of pieces of work that we've been doing in the context of the Open Geospatial Consortium, but obviously with the partnership that they have with TC211, this is applying ISO standards, and it's a couple of international in focus, and have included quite a few organisations. I don't think that that's a comprehensive list of all the people that have been involved, so I apologise, but if their logo's not up there, they're probably not very important. Actually, that's what I told Niwa when they said our logo's not up there. But so what I'm going to do today is set a little bit of the context about why we are doing this work, and then I'm going to talk about an interoperability experiment to advance the standardisation of soil data exchange, and another one that kind of spun off it in an oblique way around linking together environmental feature data, and with a little bit about where next. So the context, mainly for the soil side of things, is we've got a real problem at the moment, and that we have a soil resource that's under a huge amount of pressure, with increasing population and intensifying activity and so on. And it's an incredibly complex beast that we just do not understand well enough. It varies so widely over such a small distance, and we don't have enough data to properly characterise it. So we need to get as much data as possible out there. And to support that, we want to have a method for actually exchanging and sharing it. So we see the use of standards is a really important way of pulling this stuff together. But really, we did this work focused on soil. You can cross out soil and you can pretty much add in any other feature, whether it's a river or a catchment, an aquifer, or whatever. So part of the context of this is we're trying not to think in isolation. We're trying to look at standards in a whole of environment context. I won't go too much into the Open Geospatial Organisation, because I'm hoping most of you know what the OGC is. There's 6 members here in New Zealand. But the important thing here is the interoperability experiment, the thing that we're actually running. And I call them standardisation by doing, and I like them because they're meant to be very quickly run with minimal impact on the people that are participating, but have formal structure, and there's got to be a real reason for doing it. So you're meant to be attacking real problems and coming up with real solutions for things. Ultimately, if it all works out well, then a standards working group spins off them. So the Soil Data Interoperability Experiment was convened out of the International Union of Soil Sciences Working Group for Soil Information Standards. It was initiated by CSIRO ourselves, who also provided the management, the technical leadership, our participants from Australia, the US and Europe. And the idea initially was basically to reconcile 5 existing standards into a single standard. And that's usually the point where people panic, because this XKCD cartoon is quite correct. But we did actually have a point to prove in here, which was some of those 5 standards didn't need to exist in the first place, and we could go back to existing standards. The use cases that we looked at were around integrating data and publishing it, so the standard interoperability one, mobilising soil sensor data, so a time series use case. We also wanted to look into modelling of properties and predictions, so actually generating new data off the data that we're exchanging, which leads into things like petatransfer functions, which are little algorithms that soil scientists run to predict, say, bulk density when they haven't measured it, but they have got other controlling phenomena that they can use to predict it. We looked at a bunch of existing standards at the end of it, and this was quite a heated process because, if nothing else, standardization is a social beast. Ultimately, we had no clear candidate to run with. The idea was hopefully we'd just go, that one works, let's formalise it. So we had to go back to basics. One of the things that we tried to do too was to actually do our information modelling without getting too caught up in the technology that would be used to do it. And I think that's a pretty important thing, because one of the really awesome things about the OGC are the domain working groups that it pulls together to actually define what things that we're dealing with and what their properties are, giving us those abstract models for the behaviour of systems that we can then actually implement using a variety of tools, because there is no one right way to do things. And I think if we were to formalise it but then say you can only implement it using a GML application schema, we've killed ourselves really early on. So what did we do? The first thing, we looked at soil observations. So here it was dealing with the little bits of soil that were taken in field and then taken off to laboratories and tortured by machines that go ping and then stored in archives. We proved what we knew was the case already, which is that I've got to have my one ISO 1900 series number in here, but 19156 observations and measurements could do pretty much everything that we needed it to do for exchanging those data. The next bit we looked at was real-time data coming from in situ sensors in the field, and again we had been involved in the development of the time series profile of observations and measurements, which, for those of you that love these things, was basically derived from WaterML2 Part 1. And we proved that we could use this model to actually mobilise time series data. So that's it. 2 existing models do almost everything that we need without having to stamp it with soil as a, to, I guess, claim ownership of the model. Where we did start to go it alone was coming up with a model that defined the actual soil body itself and its constituents. And by this stage, we'd more or less run out of time. So we came up with quite a simple model of the soil being broken down into horizons made up of bits, but also being classifiable. So the soil as a whole can be classified according to some sort of taxonomy, and as can the member horizons. And then it's an IE, so we have to implement it. We have to prove that this thing works. So we implemented across 2 technology stacks. Better projector this week. That green wasn't green on Monday. So the green stuff are the ISO OGC suite of service interfaces that we used from. I actually asked the question in the presentation on Monday, how many of you people know what these acronyms mean? And no one stuck their hand up, which surprised me. I didn't expect that many. Although there were a couple that did know what they were and were too scared to admit it. But so yeah, we ran the WFS as a way of providing the structured observation data. So effectively it was our database interface. We ran sensor observation services to provide the time series information. We deployed processing services to publish the algorithms that we use to take data from either the feature service or the sensor observation service and do the execute the petatransfer functions to predict values. And then we also presented predicted stuff like variation in soil properties over space as gridded data, not DGGS approved, sorry Robert and Matt, but using web coverage services and also simple precompiled maps from the map the map service. So far, so good. So much sort of the current state of the standard stack. What we also brought into it was a tentative foray into linked data, where we gave everything HTTP URIs as identifiers. We broke things down into as smaller objects as possible when delivered by services, and using a persistent identifier service, the same one that same stuff that Margie presented before, a nice piece of kit to come out of the Ozscope initiative. We stitched all those together using this tool, and we also had to handle the definitions, the vocabularies that we use, the properties that we define, the taxonomies and so on. So we took a registry service that CSIRO had stood up and used that. And then we put all of this together in a set of clients, which I'll quickly show now. So our first demonstration, this is a Shiny app that pulls together soil moisture, soil temperature and rainfall data, in this case from a network of sensors deployed by Horizons Regional Council. You can just imagine that there's another two as well, one pulling together sensors from the USGS flood hazard modelling system in Wisconsin, I think it was, and a research farm of ours in South Canterbury. The next bit was around soil property services. So this is a coverage presenting concentration of organic carbon in the top 5 centimetres of the soil in QGIS, and here's the map version of that in a web viewer. And then finally we got into the big one, which is kind of like the integrating one, where we pulled together our field observation, sampling, lab analyses and that kind of thing, the things that we do when we put podologists in holes and don't let them out until I've described everything, and then analyse it. And we pulled together data from across the world, partly because of Dutch megalomania. We were able to get more or less global coverage out of the ISRIC World Soil Archive, which is what you can see in, green. The blue stuff is CSIRO's data from the eastern states of Australia, and way down in the bottom right hand corner there's actually a website you can go to, maps that don't have New Zealand on it. It's quite worthwhile. This one actually had it, and that's our stuff. There from our National Soils Data Repository. For each of these things, so each dot recommends either one or a cluster of soil samples, and here's where the WFSNet kicked in. We were able to find and filter those spatially, zoom in, and then once you got into these things, you could click on them, and then it was a matter of following the links to the related data. So you got the specimen, and then you could click on a link and get the horizon that it had sampled. I apologise for the quality of the sides, showing some of the properties, some visualisation of soil composition. And then if you clicked on the green button, that submitted a call to a web processing service, just providing the URIs, that the processing service then dereferenced those, pulled back the data. In this case, it predicted bulk density, plant wilting point, hydraulic conductivity and field capacity of the soil. And underpinning all this was a definition and exploration of values. I'm going to go way over time, sorry Richard, I'll speed up. Using the register and the simple knowledge organisation system to define our vocabularies, but also our properties and so on. So look, it went well. We got a simple model out of it. We could harmonise structure, we could do the basic interoperability thing, and manage the semantics of the data that we dealt with. Nice point to then move on to actually getting a proper source swig up and running to define the model better. But alongside this, there's a young guy called Dave Blodgett who's about 8, I think, but is extraordinarily enthusiastic, and if he's not the head of the USGS in a couple of years, he'll be president, one of the others. But we had a chat with him, and he came at it from the thing about, well, how do we, you're doing this linking business, how do we link all of our environmental data? And how do we do it in a way that he describes as being the HTML for environmental data? So there's two things to that question. The first one, which is a bit easier to answer, the first question is basically bringing together environmental data. And we've talked a wee bit about the motivation for standardization in here, and for me this is one of the big drivers, is there's almost no environmental data out there that has any really profound meaning on its own. It needs to work in context. If you take a digital soil mapper, right, they're predicting the variation in soil, and they're using it as a function of a whole bunch of environmental variables. Not all of them are actually, the character of the soil itself. And in most of the other problems that we deal with, you need to understand the interplay of geology or soil or climate and to be honest, social and economic factors as well. So we've got to integrate data together, and we really have to lower the integration overhead, because it's a nightmare trying to pull these things together, said the data integrator. I'm only 24, but I look like this because of data integration problems. That's why I keep telling myself every morning. The second bit, I mean, what the hell is this HTML for environmental data? Basically, what Blodgett's trying to get at is we have this pervasive technology between HTML and HTTP that is used without thought or controversy. People just use it. When you come up against the services that we work with, there's a school of thought that the GML-driven and 19100 series protocols are a bad thing. They're too difficult to deal with. Meanwhile, we've got REST and JSON, which sort of fit nicely in this environment, and they're great. To be honest, in part it depends on your perspective, and it's not an argument that I like to buy into, because there are more than one ways of doing things, but there are some cool aspects of this. So if you imagine taking your environmental data and actually having it findable on the Google web, searching for a monitoring station by name, and you would get the results. And then wouldn't it be cool if we could actually have some description of it turning up in the Google Knowledge Panel alongside it? But more importantly, which is what David was running with, is how do we find out about the related features? I've got a monitoring station. Well, what river reach is it actually sampling? What river? What are the reaches upstream and downstream of that? What river is it on? What's the catchment it's in? Or I've got a soil moisture sensor that's monitoring something in a paddock, which contains this irrigator, which is sampling this aquifer, which then is influenced by this catchment. How do we build together this web of stuff, knowing full well that these are not going to be stored in one location? No piece of data is going to know about everything else. So how do we pull together this graph? Now, that's a standard interoperability problem, but we're looking at doing it in a way that is friendly to the current set of web developers. This isn't one answer to fix every problem, but there is a huge community out there that wants to use this data and use it and use it in their systems with a minimal time to understand the protocols and that kind of thing, and we need to work with them. So, no unusual formats or bewildering data structures and that kind of thing. We don't want them getting scared and angry when they see a square bracket. But we have to be disciplined, right? When we define these things, and this is the other reason why we standardise stuff, is every time I make a call to that resource, I want the same thing coming back. If the data changes because the thing has changed, cool. But I don't need my carefully constructed application to break simply because I've changed the type or moved from YAML to JSON or whatever. So here's where we get to the environmental link feature interoperability experiment. Now, we were hoping to demonstrate this at the upcoming TC meeting next week, but it's not finished, which means I can't say too much about this, because otherwise Scott will shout at me, and he can shout really loud. So I can only give a sort of a high-level view of it without getting too far into the weeds. But it comes out of the USGS. The technical leader is here in New Zealand. It's Byron Cochrane. He's not here, somewhere. And BAGM in France initiated it, and then there's a few of us here in New Zealand and some others in the US and Australia that are working on it. If you Google OGC and Alfie, you'll find links to their GitHub repository, and there is a process that you can go through to sign necessary agreements to actually participate. So if you're interested in this, take it further. The OGC's been working with the World Wide Web Consortium to develop a set of best practices, and we thought this was a good opportunity to try those in here for spatial data on the web. Particularly best practice number 1, but using persistent URIs for spatial things. Now, this is essential because this is the engine of the whole system. This is the link. But so you can kind of think of it as RESTful. Hit a link with an HTTP GET request. You use the right headers, and you'll get stuff back. But it has to be disciplined. Basically, in this case, the links can't rot. Right? If you're building up a distributed commons of data, you can't have broken links. The second bit is to come a bit closer to the data formats that people want. So use the likes of well-known text and that kind of thing for your encodings. This one here is around using spatial data through convenience APIs. I call it keep it simple, but it's a bit more complex than that. But basically, if there's lots of requests that people make and there's an enormous Sparkle query or something like that you have to run with it, we'll proxy that with a little convenient API that people can just hit time and time again. And then there was another one down here which I think is quite important about make your spatial data indexable. And it's something that everybody else, I think, on the web takes for granted, but we don't really do particularly well, which is, let's have HTML landing pages for our data and mark them up with structured data that helps the robots search it, find it, populate the knowledge panels and that kind of thing. The other advantage is it doesn't take away the need for them, but it reduces our dependence on specialist registries and catalogues, because you could potentially just Google stuff and then find the catalogue and then get more information about it. Needs to be disciplined. We need standardised content, so we can't get away from having to have some sort of formalism. And in this case, we picked JSON-LD to do it, because what that is JSON-LD files, they look like, it's JSON for linked data. They look like JSON, but they've got a link to a context file, which is sort of, if you say it really quickly, like a schema, which binds the JSON keys onto an ontology. So you get a hook into your formalism there, but without creating something that looks like Turtle, or again, one of these formats that scares people. Can't say too much more about what we're doing with it than that. We're taking a variety of use cases very quickly: water quality, agricultural issues, and a few more like that. There's a bunch of demonstrations we're doing, but again, I could show you more, but yep, I'd had to get Richard to kill you as you left. It is actually going quite nicely, but we just weren't going to get it finished for this TC. So the preliminary results, we can kind of use JSON and REST as, let's say, an entry-level linked data. As entry-level linked data, we can link stuff across services. Great shock. It's the web, We're the first to work out how to do this. We can index stuff. Standards-wise, there's some really useful core ontologies that have been developed out there that we can actually use for this common stuff. The W3C working group has things, or W3C has SCOS, the joint working group with spatial data on the web has come up with things like the sensor, observation, sampling and actuators, SOSA ontology, Altime and that kind of thing. But also there are really useful OGC applications schema that we can use, particularly for building relations between things. Water ML2, groundwater things, GeoSciML, high features and so on. But not all of those are RDF ready, so that's a bit of a problem. We don't by default have ontologies for those. But we're solving a mass market problem. But it is important to say that this doesn't meet all needs. So there will be like power users interfaces that will have to deal with it. What comes next? Not really sure. Source standards are a bit of a problem because we're mired in social and political issues trying to pull things further. Alfie, I'll tell you when we finish it. But there's some really interesting follow-up projects that we see with it, and we also see this as a nice sort of gateway drug where you can work with your JSON and your RESTful practices, and it's quite nice, and then you can start to discover more and more of the standards base and the rigor that gives you, and hopefully that'll help with adoption. One of the things that we know out of it is the semantic web, and this formalised thing will be quite a useful part of the future, and this is kind of where I segue to the presentation that Horizons. Adrian and Sean are going to give, because that's an example of a lot of the stuff that we've been faffing around with in here actually realised in quite a nice system. So that's where I'll stop.